I wanted to go through the homework for this week. I had originally planned to go through a couple papers, but there seems to be plenty in this one paper. It's an old paper. I just wrote a proposal on these asphaltenes, so I had this paper around, but it seems to have quite a bit of what we're going through. I mean, I showed you last week the scattering, the neutron scattering, or these are X-ray scattering, X-ray and neutron. And we went through, like, there's a prod part of power 4 and then a power roughly 2 for the aggregates of these stacks of graphene molecules. The graphenes are can be, like, if you take the sand tar from Canada, I think it's something like 80% graphene, and graphene is a mixture of different aromatic, polyaromatic hydrocarbons. And so usually they talk about it. The average one would be like seven of these aromatic rings, and then there might be like some hetero rings in it, either nitrogen or they could be sulfonate and oxygen. Right? So one molecule wouldn't have all three, but something like that. Right? So, and then you can also have alkyl chains off the side. So kind of like a 12 carbon alkyl chains, that kind of thing. Every molecule doesn't have all those features, but basically they'll all have this polyaromatic hydrocarbon part. So these are benzene rings. So it's got you can switch between those two. These can hop over. So the thing's actually got a ring current to it. And those are planar. So those rings are kind of a cloud. So they're going to be about 4.5 angstrom and then maybe 6 angstrom in diameter. So they aren't, you think of it like a plate, but actually it's kind of a lozenge shape. Right? But this, since these are conjugated bonds, they have to be in the same plane in order to flop the electrons around. So basically this entire structure is planar. So it acts like a card, kind of a thick card. Right? And then these ionic groups are going to have like charges on them. And then these groups can also have phenolics. You can have a phenolic on this, like an OH sticking off. So these are hetero rings, and that's a phenolic, which would have a negative charge, del negative to it, and then alkanes sticking off. Right. So it's basically it's the only part of oil that's polar. So if you put the oil into heptane, into any of the alkanes, so like C5 pentane, which is the lowest molecular weight alkane that isn't a gas, right? Propane's a gas, and then hexane, pentane isn't, and then heptane is the other one people use, and octane. It's 8 carbons, right? So if you put oil, then this stuff precipitates out. If you put it into alkanes, and then if you can take, so you can wash it with the alkanes to get just the asphaltenes, and then you can solubilize that into toluene. And so that's like benzene with a methyl group on the side, or xylene. You can use ethyl group on the side. And so the aromatics stack. So these, you get this is called a pi bond and an aromatic, and you get a pi-pi stacking. So these asphaltenes, if you purify, will just form stacks, and those form nanoparticles. Then those nanoparticles aggregate into these mass fractals, and I think the dimension is 2.5 2.5 mass fractal dimension for this thing. Right, so that's kind of the structure. Then these things go on to form agglomerates, and the agglomerates go on to make a network structure that clogs up pipes. And if this shows up in sand, so between the sand particles, this stuff will glue the sand together. So tar sand in Canada is like their biggest oil supply, I guess. In order to separate these, you have to do crazy things, like steam treat the sand to get the oil out, which leads to an enormous mess, right? So, yeah, so you'd want to figure out how to prevent asphaltenes from aggregating. So the stacking isn't a problem. The aggregation isn't necessarily a problem. It's these clusters and networks that form that's a problem on the order of like 10 micron to meters, right, to a large size. But it's built on this hierarchy going back to these stacks. So if you can prevent the stacking, you won't get the primary particles, and you won't get the aggregation, and you won't get the agglomeration, you won't get the networks, and you won't get the clogged pipe. That's the idea of the asphaltene studies mostly. Anyway, so they do sands. So in this size range, you can see the stacks over here, the solid objects. Power of -4 gives a surface to volume ratio. Then there's a roughly power 2 for the fractal aggregates, which are here. If you could go down further, you could see that there's agglomerates of these aggregates, and then other things happen. Right? So we talked about that last week, the scattering. So if you put these, if you purify the asphaltenes and then put them into solution in toluene, then you can do dilute solution studies of the things. Okay, so that's the idea here. So they put these into solution. What the concentration is, but I think it's 2%, down to 0.5 weight percent for sacks, 0.3 weight percent for sands. So anyway, they're doing dilute, so they have these isolated particles, and they can look at the concentration dependence of the scattering. And again, we talked about in class that that you're going to have like an average density in the material. And then if you're at size scales, so if we're at size scales larger than the aggregates over here, so it's called I naught for the 0Q intercept, then you're really looking at these, you're looking at the system as a continuum. And then within that continuum has an average electron density for X-rays. And then there's fluctuations about that continuum that are driven by KT. Like in other words, the aggregates will diffuse until they finally kind of cluster. So you have a high density, and then they'll disperse because they have repulsive interactions, and that leads us to fall back down. Right? So you can have depleted regions where you have low electron density, and then there's an average density for the sample, and you have high regions, and that changes with time and with space, both. Right? So you have these fluctuations that are going on. So if the concentration gets higher, you have an increase. So you can think about these particles as a gas. So the solvent disappears, and you just have floating around particles, colloidal particles. Then you can think about a pressure associated with that. And then if you have a pressure, you talk about the ideal gas law to describe the pressure. So this is number per volume, so PVs and RT. So that's a concentration. And then if you want, you can expand this to include the Bureau coefficients, right? So you have P RT times 1 plus the density times the first Bureau coefficient. So, and then you can go on to higher orders, but usually the first is all, the second Bureau coefficient is the only one that you use. If this is a polymer, then it's not mass. You have to divide by molecular weight because each of these particles has a molecular weight. So this ends up being 1 over molecular weight here as first prefactor, because each particle isn't a mass of 1, it's a mass of a molecular weight. So anyway, if this is volume percent, volume fraction, then this B2 is the excluded volume. So for polymers, that's chi 1/2 minus chi times the volume of a monomer unit. Right? So if this rho is mass per volume, so concentration and mass per volume, then this number, so you use C instead. So you have C RT, 1 over molecular weight, plus C times A2. Okay, so there's two ways to talk about the Buell coefficient. B2 has units of volume. It's more or less the excluded volume. It's excluded volume plus it's this enthalpic interaction. So you have the hardcore volume and then whatever kind of repulsive things that it has with it. Right. So this B2, if you write in terms of the van der Waals equation, is the excluded volume minus A by T. Right? So the van der Waals expression was that the pressure is the volume minus B, and then RT, and then minus A by minus A by B squared. So that's the van der Waals. So you have this attractive interaction that lowers the pressure, and then you have a repulsive excluded volume term. And so you can write this B2 from this expression for pressure by rearranging this, and you get the B2 is B minus A by T. A is the enthalpic attraction, and B is the excluded volume. Right? So anyway, in terms for polymers, this becomes 1/2 minus chi times this volume exclusion per monomer. That's B2. And then it would have units of volume. And then A2 has some odd units because you have to convert to mass concentration instead of volume concentration. Right. So it turns out that this pressure is called the osmotic pressure, pi. So if you have you talk about an osmotic compressibility, so you can say, how does a volume change? So you can talk about the change in volume with respect to concentration. Okay, so or change in pi, change in pressure with respect to the concentration. As the concentration goes up, you get a higher pressure that forces this to go back down. So that d pi dc or dc d pi would be the osmotic compressibility. Right, so the intensity is going to be related to how the pressure changes with concentration, but the osmotic compressibility is 1 over that. So you have the intensity is going to be 1 over this dc d pi number, which is called the osmotic compressibility. So this pi you can write in terms of the Flory-Huggins equation, and that's how you get this 1/2 minus chi, and you can take the derivative with respect to concentration, that you can calculate what this intensity, the scattering intensity, would be due to these fluctuations that are happening related to KT. Right, so KT drives the fluctuations, drives the scattering. It's inverse to this dc d pi, which you can calculate from Flory-Huggins equation. Right, so that's kind of the gist of this, where this term 1 plus 2 A2 molecular weight times C comes from. This comes from the Flory-Huggins equation. So, or any thermodynamic equation for miscibility. You just do the derivative with respect to concentration of the pressure, and then you can get this expression. Right? So that originates from the scattered intensity I naught at 0Q is 1 over the osmotic compressibility, right? Which is going to be dc d pi. So you calculate d pi dc, and that's going to be the intensity. Right? And that gives you this expression. So that's where that thing comes from. So what you want to do is march across. So that in the Zim equation, this is just a prefactor to the this Guinier expression. So you have 1 plus that times the Guinier, which is 1 plus q squared rg squared over 3, using the exponential of x equals 1 plus x squared over 2 factorial, right, plus whatever. So it's small x, you have 1 plus x. So this 1 plus x, and if it's exponential minus q squared rg squared over 3, then that equals 1 over exponential of q squared rg squared over 3. So the sign changes. And then that's where this 1 plus thing comes from. Right, that's Newton's law. That times this 1 plus 2a gives us that term, and then plus this a2 term after. Okay, so you take this, extrapolate to 0q, that term goes away, and just end up with 1 plus this thing that came from the osmotic compressibility. Right, and it's got A2 in it instead of B2 because the concentration is in grams per mole, is in grams per cc. Right, it's a mass concentration instead of a volume fraction. All right, so A2 is kind of an odd beast here, right? It's not what you'd expect from a Viral coefficient, which should be just volume. It's got this mass term in it too. Okay, so then he goes through a bunch of things. Like first thing he says, he defines this A2 in terms of this expression for the molecular weight. Right. So like where does that come from? So this reference 29 is this book that I put up also, and it's a chapter in a book. So it's an 83-page chapter on solution properties of branch molecules. And he goes through let's see, at the end of one of these, he goes through second Viral coefficient, A2, page 134. Right, so is that 113? Is this 121 or something like that? No, this is just 134. This is the same equation. So this paper is kind of taking things from this. This is a Newton's law, right? That Rg squared q squared over 3. That's the same equation. So he's just kind of copied this book chapter. And then 134. This is the transport, that's the diffusion coefficient, and then 32 friction factor, and then intrinsic viscosity, 133. So he goes through the intrinsic viscosity equation, and then he goes through this Viral coefficient thing. So he starts with all right, so he has this equation, which is, so R cubed, so B2 would just be R cubed, in other words, a coil size. So B2, if we have this, here, so if you have this in terms of the volume fraction, then B2 is just the volume, right? So B2 is just the volume term. So B2 would be R cubed. When you convert it to mass fraction, because it's going to be mass squared here, you end up with mass squared here. So the second Viral coefficient is times mass squared per volume. So you end up with a mass squared here also to correct the B2 to get A2. So these terms are all coming from, the m squared term is coming because A2 is in a mass fraction, not in a volume fraction. And then we know that that for a mass fractal, R to the df is the mass. Right, so if you have R cubed by m squared, then that ends up being m to the 3 by df minus 2 for a mass fractal. So his m squared R cubed becomes m to the 3 by df. So that ends up being this other equation that he gives somewhere. He gives that in the paper. So Rg is 1 by df, A is 3 by df minus 2. Right, so that gives the expression for A2 is just kind of taken from this book. You can kind of get that. What else is in this paper? Let's see. So So he gives that. This is just the mass fractal scaling. That's the normal scaling because I is like mass, Q is inverse size. You get, this is a restatement of equation 9. And then what else is in here? All right, so then he gives a bunch of things on intrinsic viscosity, which is also this week. So that's why this paper pretty much follows what we're doing this week. So despite that it's 2009, I'm still giving you this one. So intrinsic, so we have the viscosity of a solution. It's mostly going to be made up of the solvent viscosity because it's a dilute solution. And then it's going to be modified by some constant times the concentration. Right? And this is mass per volume concentration. Right? So the unit of this has to be unitless as a group. So this guy has to have units of 1 over concentration. Right? And that's the intrinsic viscosity. So it's not a viscosity, it's a concentration. And that essentially ends up being 1 over C star. So that is, if you add 1 unit of the structure to the material, then how much does it displace the volume of the system? So that's C star, like the mass per volume of a polymer coil. Right? What's the density within a polymer coil? 1 over that is this intrinsic viscosity. Right. So this means that mostly you have the solvent viscosity and you have this addition term that comes in linearly. Right. In fact, it probably should have like other orders here, right? Like a power series, like a Taylor series. But basically, at dilute enough conditions, you ignore those and you have this. And so you want to know an equation for that. So the first thing you do, divide viscosity by the solvent. Right, and that's the relative viscosity, and then subtract off 1. So subtract off that. That's the specific viscosity, and then so if I do that, if I divide that by concentration, then I'm going to get what this thing is in the limit of when concentration goes to 0. Okay, so you can rearrange this to get a variety of different kinds of viscosities until you finally get this intrinsic viscosity, which isn't a viscosity at all, because you remove viscosity because these are all normalized. So this is unitless and you just have concentration. So this thing ends up being 1 over concentration. Right. So questions in here have to do with that. This is the same equation, right? It's like kind of going down the road of, so you have the reduced and then specific, and then this intrinsic, and you can do, if you want, you can do a power series and concentration of this. That's called the Huggins expression. Right? In other words, this is just a dilute condition, and then if you want to have higher, you add in another linear term in concentration, you could do that in a power series if you want it. Right? So there's going to be another prefactor where you just say it's K times that thing squared if you want. Right, so that's just one way to do this. So there's many ways to describe like how higher order concentration is going to affect the intrinsic viscosity. So it turns out like this original equation, this guy Einstein calculated what that would be for spheres, which is a popular way to look at it. And it turns out that that thing's exactly 2.5 or 5/2 for spheres. Okay, and that's a fairly involved calculation. But nonetheless, so there's a fixed value. So you have a solid object, this thing's a fixed value. The solid object is 2.5. And all this equation does is say, if I have a fluid, right, and I'm calculating the viscosity, which is going to be this shear stress divided by the strain rate. So the strain rate being the velocity gradient. Right? So I have like a profile to this thing, and I put a force on it per area. The area is normal. It's like, so it's a force, it's like a deck of cards. If you're putting a shear force on the top one. Then the slope of the velocities in the card, bottom card stuck, and the top card stuck to your hand, and in between there's a gradient, right? dv dy is the gamma dot. So if you take gamma dot times the viscosity gives you the stress. Stress times the viscosity, the strain rate times viscosity gives you the stress. Right? That's just the viscosity, Newtonian viscosity, shear viscosity. So this equation says that if I put in spheres, they're going to take up some space in here, and that's going to make it look like I have a higher viscosity, right? Because the same change in viscosity has to happen over a shorter distance, so the slope has to go up. So even though I'm measuring a fixed gamma dot, I've displaced an area. It makes it look like it has a higher slope. That gives me a higher stress. Right? So this is just a displacement law. Like I've just volumetrically displaced the area that it could flow in. And that's why I get this increase in this overall viscosity. And if the thing you're displacing with are spheres, so they don't fill space exactly, 2.5 is the number you get for that. So you get some other fixed number, but anything that's solid is going to have a fixed number here. Things that aren't solid, it's going to depend on how large the things are. Okay, because this number actually is how much space does an object take up, right? Which is like the volume is going to be the radius cubed. And if the radius goes with the mass to the 1 by df, then this thing is actually going to be the mass to the 3 by df. Right? So in the concentration, so it's going to be units of concentration, so it's mass per volume, then it's going to have to be mass to the 1 minus 3 by df. Right? So if df is 3, that's 0, and anything that's 0 is 1, so I just have a fixed number. So for spheres, it's a fixed number. That number is 2.5. This thing is rods, right? Then this is minus 2, because they have 1 minus 3 is minus 2. So for rods, it's going to be 1 over m to the 2. And for Gaussian, this is 0.5. df is 2, so this is 1.5. So it's m to the minus 0.5. And for good solvent, it's m to the minus. df is 5/3, so it's 9/5. And 5/5 gives you minus 4/5, or minus 0.8. Right? So for rods, I have minus 2. For Gaussian, minus 0.5. For good solvent, minus 0.8. Right? So you could do other objects if you wanted to, but basically this is how that intrinsic viscosity is going to depend. So that's the Markovic equation. Intrinsic viscosity is some constant times the molecular weight to some power, right? Like that. So that's kind of the way this thing works. Here you've got the 3 by df minus 1, which is what I should have gotten out of this. But anyway, so that's the right equation. So anyway, so for spheres, it's 2.5. And then he gives those two equations. Then he gives, this is a sphere equation at 5/3. And then most we have the original equation. This equation is a fractal equation. This is just the Einstein equation. And then there's this equation. Okay, so this one's a little bit different than that. I don't know why this guy always shows that. This one, so here, if you take this thing, 1 minus intrinsic times concentration, then you get the reduced is the viscosity over 0 is going to be 1 minus intrinsic times concentration. And we know that exponential of x is 1 plus x over 1 factorial plus x squared over 2 factorial. And at small concentration, we can compare those two and say that that thing is exponential of minus intrinsic times that at low concentration, right? And then you can take his equation 18, and say that he's got in R is 1 minus phi over phi m to the minus 2, right? So this thing we could say at low concentration is e to the minus phi over phi m, right? And then it's 1 over that, or 2 over that. So it's that thing squared, which equals e to the minus 2 phi over phi m. And then it's negative, so it makes this thing plus. So then I can say, that I can equate these two arguments, and I can end up saying that then my intrinsic viscosity equals 2 over this phi m somehow, right? And I already said that intrinsic viscosity is 1 over c star. This is also a concentration. That concentration, he says, is phi m is the dense random packing limit fraction. So this is a Quimeta equation. Right? So this is just the same equation written in a different way. Right? So basically, this is phi m is something like the overlap concentration. And so this probably is only useful at low concentrations because you had to use this exponential thing to kind of work this out. So there's that business. And then, so the questions are mostly like that. Equation 6 is basically a sim plot. I went through that. And then the intrinsic viscosity is this Taylor series. Show how equations 15, 17, and 18 are obtained. So that's 15 is just the definition. 17 is the Einstein equation for a solid object. And 18 is what I just did with this exponential thing. And then explain the origin of 16. 16 is this just the mass fractal law. So you say that this, say that this thing is 1 over c star. C star is the mass over the volume cubed. And then the volume, that's going to be the mass to the 3 by df, and then minus 1 for this one. So that's that equation, right? And then what else is here? Then the power laws observed in equations 9, 20, and 21. Okay, so equations 9 is just the fractal law. That's just the mass fractal law. 20. So 9's kind of a definition. 20, this comes from this 3 by df minus 1. So if you say 3 by df minus 1 equals 0.41, then you're going to have this thing's 0.59. So df equals, let's see, oh, this becomes plus 1. So 1.41. So 3 over 1.41 becomes df. So that's something like 2. Right? You're going to get roughly 2, a little bit 2.1 or something for df. From that, right? He gets, so he's getting 2.1 for df here, right? So this is just like working out that equation to find df for that power law. 21 is a thing for A2 that we got before somewhere here. 21 I got already for some function for A2, right? A2 m is this thing. So it's r cubed over m squared gives m to the, let's see, r is m to the 1 over df. So it's going to be 3 by df minus 2. So in that case, he's got a value of negative 55. So 3 by df minus 2 equals negative 0.55. So this is 2 plus that, so that's 1.45. And then df is 3 divided by 1.45 is df. So that's also about 2.1. Almost the same thing. So that's just using this law, right, for A2. And then so that's those three things. I mean, it says like find those three things, figure out what the value is. Blah, 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 blah. The brochure book. So look at that chapter in that book. Yeah, that's that part. And then E, the main problem with asphaltene surface deposition. Then he goes on to study the surface, or he reports on what he already reported on. So he's got two other papers, 4546, where he did this. He took, so the problem is the deposition of asphaltene onto surfaces, like in pores of sand to make tar sand. Then he wants to measure that. So he gets some spheres, and then he sticks them into asphaltene, and he lets the stuff deposit on it. Right. So then he gets the mass of what deposited. And he wants to know how does that mass deposited, which is this gamma, so that will be a function like gamma versus time. It'll start at 0 and it'll gradually increase with time. And finally, he says he reaches a plateau. So the assumption is that plateau is if you have the sphere and then its surface is covered by these aggregates, like each of those is some kind of aggregate of asphaltene. Right. So you have this idea that you have a monolayer, right, of these aggregates around the surface. So the surface area is the number of aggregates times the radius of an aggregate squared. And then this is going to be mass, and the mass on that is the number times the radius cubed, like the volume times that times the density. And then you're going to end up with something like this equation, like the molecular weight over the surface area. Number times the area squared gives you the surface area. Number times the mass gives you the mass. And R is the mass to the 1 by df. So if you plug that in, you'll get this equation. Right, so that's kind of a monolayer equation. And he gets pretty much that behavior from it. He gets a power law behavior, so it's a log-log. Should be a log-log plot. I guess that's log-log. See 4 to 5 smaller than 1 to 2. Anyway, so he gets a power law dependence. He gets the slope 0.37. It should be 1 minus 2 by ds, but that doesn't work out for him. So he's got 0.37 is 1 minus 2 by d, should be df. Right, so this gives you what, 0.63 equals 2 by df. So df is 2 by 0.63. And that's going to be something like less than 2 or bigger than 2. What is it? So it turns out it's not the right number that he wanted. It ends up being about 3. Right? So that's too large. He wants 2.1, gets 3. He says that's because when these aggregates hit the surface, they collapse down into like solid objects, something like that. So it's ds close to 3. So anyway, that's kind of the gist of this thing. Whether that's true or not, I mean, that's kind of hard to tell. So that's kind of, it's about asphaltene. They're macromolecules, but not exactly polymers, but they're macromolecules. There's some similarities. Anyway, they're colloids of some kind. And anyway, it takes into taking a look at this Prerecorded book chapter, which is similar to what we're covering in class. So you can take a glance at that and see if it makes any sense. If you have questions on that, we can go through it. And then there's also a chapter in here by, this is a pretty good book. So it's one of these topical books, but the chapters are really long. So it ends up being like 3 separate short books hooked together. And the other book is, it goes through RG by RH. He goes through everything useful here. Like RG by RH gives the values for it for different kinds of structures. This is a pretty useful chapter, this Burchard thing. Burchard's a pretty famous guy from Freiburg. I mean, not sure he's around anymore, but basically it's an important chapter. I think it's one of his main things. And then McLeish and Milner. So that McLeish is kind of like the leader of rheology in the UK, and Milner is the guy from Exxon that does simulations. So these are the two of the top guys in polymer rheology. So it's a pretty good chapter at the end of this too on branch structure, how branching affects flow, essentially in like polyethylenes. So that's also worth looking at. We'll talk more about this stuff later on, I think, but it shows the typical thing, like you have a flow regime at low frequency, and then you have plateau modulus, and another crossover at high frequency. We already talked about that, so you might want to glance at that chapter too. So there's a bunch of things to look at. You don't need to look at all of it, but basically, if you have the time and you want to, you can glance at those two. Then this paper's, I mean, everything in this paper we've kind of covered, so it's kind of useful to know it's not exactly polymers. And that's pretty much it for this quiz. So hopefully it's not too bad and doesn't take up too much time. Sorry to give you something over the break, but in the fall I skipped all the homeworks when we had breaks, and that ended up not being very good. So I think that I've gone to this homework mode since the pandemic, so, and it seems to be a pretty good mode to go to. And but basically you can't skip. So basically it'd be better if we just do this homework this week. Hopefully it won't be too big of a burden on you. Anyway, so that's about it. If you have any questions, just email me, or basically email me. I'll get back to you. Hopefully this won't be too hard to do. It's a lot of like derive the function things, which the undergrads haven't been particularly good at, but the grads seem to have done well. So if it seems to be like overwhelming, either email me, let me know, or whatever. Don't worry too much about it, but it'd be good to, I think it's pretty reasonable. When you see equations, you should be able to sort out like where they came from and what he's talking about. These are some pretty simple ones, fairly simple ones that you can work out. That's about it. So again, like, email if you need any help. Hopefully that's okay. Sorry I missed on Friday, but I had that proposal I had to send out. And that's about it. So I'm going to quit here. Thanks.